Okay, hello everyone. Welcome to the fourth session of the SLE training series titled IRT Linking, featuring Dr. Kyung Yong Kim from University of North Carolina at Greensboro. My name is Stella Kim, and I'm one of the co-chairs of the SLE with Jamie Malatesta, the other co-chair. First of all, I'd like to thank everyone for joining this session today. Hope this session is helpful and informative to all of you. I will be monitoring the session and helping with any technical issues. If you have a question during the session, please type your questions into the chat box or hold it off until Dr. Kim opens up the Q&A session. So I'm gonna send the mic to Dr. Kim now.
Okay, good afternoon or good morning or good evening, depending on where you live. So welcome to the SLE SIGME training series. I think this is number 4, IRT linking. So I'll share another slide. So I told Dr. Stella Kim that I'll introduce myself. So. So I'll briefly introduce myself. My name is Kyung Yong Kim. My first name is Kyung Yong, even though there's a space between Kyung and Yong. And I'm a faculty member in the Educational Research Methodology Department at the University of North Carolina, Greensboro. This is my 5th year. And before moving to North Carolina in 2017, I lived in the Midwest. Now, I have a quiz before talking about linking. So which state did I live in? So the state produces more corns than most countries in the world. Nearly 1/3 of the nation's hogs are raised in this state. Human population, just over 3 million. Hog population, 21.2 million in this state. There are more chickens living in this state than people living in California and Texas combined. Hens produce close to 15 billion eggs a year. That is enough eggs to feed everyone in the world an egg for 2 days. Now, the state is the future birthplace of Captain James T. Kirk. He's the captain of the starship USS Enterprise in Star Trek. And this state hosted its very first MLB game on August 12th this year at the Field of Dreams. Can anyone guess what state this is? You can leave. Yes, it's Iowa. So I graduated the University of Iowa in 2017, and I studied with Dr. Stella Kim. Now, believe me, this slide is going to be the most interesting slide among all the slides that I go over today. Okay, today I'm going to talk about linking. And so I'm first going to talk about why we need linking. Then I'm going to talk about linking methods based on separate calibration. So I'll talk about 4 different methods: the mean method, the mean sigma method, the stalking lord method, and the Habara method. And if we have time, I'll briefly talk about concurrent calibration and fixed item parameter calibration. Now, first, the notation, theta in my slides that denotes person parameter, which is often called ability in educational measurement. A denotes the item discrimination parameter, B, the item difficulty parameter, and C, the pseudo guessing parameter. So I'm going to use the 3PL model today. Now, the first one is, why do we need linking? And if you have any questions, you can use the chat box or feel free to interrupt me. So I'm okay with answering questions. So linking has a lot of different meanings in educational measurement, but today I'm going to use the word linking to describe explicitly the process of placing all the IRT parameters, including person and item parameters, on a common scale. So that is what I mean by linking in this training session. Now, linking is a statistical procedure that adjusts for group difference in IRT, and we'll talk more about this in a little bit. And linking is only required for the common item non-equivalent groups design, or the NEAT design. Now, one of the previous training sessions was about equating, and equating is a statistical procedure that adjusts for differences in form difficulty. So linking and equating are two different things. And equating is required for all data collection designs if forms have different difficulties. But linking is only required for the common item non-equivalent groups design. And equating is based on raw scores. Now, I'll first talk about the invariance property of IRT. I believe you all know this property. So it means the item parameters are group independent. So it doesn't matter which group takes the item parameters are going to be equal across different groups of people. So in other words, the correct response probability of an item only depends on the theta level. It doesn't matter how many people are on that theta. It doesn't matter how many people are on other theta. So basically it's saying it doesn't matter what the distribution is. If a person with the same theta, they come from two different distributions, they should have the same correct response probability. And for that to happen, the item parameters should be the same across groups. Now, that's about the item parameters, but we never know the item parameters. We only know the item parameter estimates. So based on the invariance property of IRT, item parameter estimates will be similar. They're not going to be identical because of sampling error, but they should be similar across different groups of people. Now, equivalent and non-equivalent groups in IRT. So in IRT, if groups have the same theta distribution, they are referred to as equivalent groups. So for example, if group 1 has a standard normal distribution and group 2 has a standard normal distribution, then we say that the two groups are equivalent. If two groups come from a different distribution, then we say that the two groups are non-equivalent. So for example, if group 1 comes from a standard normal distribution, but group 2 comes from a normal distribution with mean 1 and standard deviation 1.4, the two groups have a different theta distribution, so we say that the two groups are non-equivalent. And we only need linking when the groups are non-equivalent, because linking is trying to adjust for group difference. So let's look at the equivalent groups case. So I made up a 40-item test with multiple choice items, and I gave the test to two groups. Now both groups, they come from the same distribution, which was a standard normal distribution. And I calibrated the items for group 1 and group 2 separately. Because the same test was given to the two groups, the item parameter estimates should be similar across the two groups. And if we look at the two plots here, the one on the left is the discrimination parameter estimates, and the one on the right are the difficulty parameter estimates. And as we can see, and the x-axis is group 1, the y-axis is group 2. So based on the invariance property, we expect the points to be near the identity line, and that's what happened here. So the discrimination parameter estimates and difficulty parameter estimates, they are closed. They are scattered around the identity line. So no problem here. Now, the second case is when the groups are non-equivalent. So a 40-item test, again, it's a different test, was administered to two non-equivalent groups, and the sample size was 3,000 for each group. Group 1 ability, it follows a standard normal distribution, but for group 2, it follows a normal distribution with mean 1 and standard deviation 1.4. So the two groups are non-equivalent. But still, we expect the item parameter estimates we obtain from the two groups to be similar to each other because of the invariance property of IRT. Now let's see if that's the case. If we look at the figures, that's not the case. So the discrimination parameter estimates, which are plotted on the left figure, they are all above the identity line, which means the discrimination parameter estimates are larger for group 2. Now, the difficulty parameter estimates, which are on the right, they are all below the identity line, which means that the difficulty parameter estimates are smaller for group 2 compared to group 1. Now, we did not expect these results because we have the invariance property, but this is what happened. So we're going to talk about why this happened and how we can fix this problem. So according to the invariance property of IRT, we expected the item parameter estimates to be similar across the two groups. This happened for the two equivalent groups, but for the two non-equivalent groups, the item parameter estimates were not similar. So the question is, what happened? Now, in IRT, theta is a latent variable, which means it's unobserved. So there's no natural scale. We don't have a natural scale for theta. So it's like temperature. There's no natural scale for temperature. That's the reason people came up with 3 different scales: Celsius, Fahrenheit, and the Kelvin scale. And they are all trying to measure the unobserved variable temperature. So we have to do a similar thing. And different people can come up with different scales. That's totally fine. But in our field, what people usually do is they typically choose the theta scale so that the mean and standard deviation of theta are 0 and 1 for the group at hand. So there's going to be a group of people that took the test. There's going to be a distribution for the ability. We assume that distribution follows a standard normal distribution. So we're assuming that the mean of theta is 0 and the standard deviation of theta is 1 for that group. Now, by doing that, 0 becomes the origin of the theta scale, and 1 becomes the unit of measurement for the theta scale. So if someone is at the origin, then that person has the mean ability. If someone's ability is 1, then we say that that person is 1 standard deviation above the mean, which is the origin of the theta scale. Now, this causes no problem for equivalent groups because the groups are equivalent in terms of their ability distributions. But this causes a problem for non-equivalent groups. And the reason is because the groups are non-equivalent because their theta distributions are different, but we are setting the distribution for both non-equivalent groups to a standard normal distribution. So although the means and standard deviations of theta are different across groups, the means for both groups are set to 0 and the standard deviations are set to 1. And this is causing a problem. So what happened is the item parameter estimates we saw for the 2 non-equivalent groups. So the item discrimination parameter estimates were larger for group 2, and the item difficulty parameter estimates were smaller for group 2. The reason that happened is because the items are on 2 different scales. One scale based on group 1 and another scale that is based on group 2. So what that means is we have 2 theta scales, one for group 1, one for group 2. Now, both groups, it was assumed that their ability distributions follow a standard normal distribution. So the origin is 0 and the unit of measurement is 1 for both groups. But the problem is the meaning of the origin 0 and the unit of measurement 1 are different across the 2 non-equivalent groups. So they're not the same 0 and they're not the same 1. Even they're the same number, they mean different things. So for group 1, the origin 0 of the theta scale is the mean of group 1's theta distribution, which is 0. And the unit of measurement 1 of the theta scale is the standard deviation of group 1's theta distribution, which is 1. But for group 2, the origin is still 0, but that 0 is the mean of group 2's theta distribution, which is 1. Sorry, no one ever calls me. And the unit of measurement is set to 1, but that 1 has a different meaning than the 1 for group 1 because group 2, the standard deviation of group 2's theta distribution is 1.4. So this is what happened to the origin. Suppose that the units of measurement are equal across the 2 scales. So we're just assuming that there's only a difference in the meaning of the 2 origins, one that came from group 1 and the other one that came from group 2. Now let's think about an item with difficulty B equals 2. Now there are 2 lines here, one for group 1 and one for group 2. Now, the origin for group 1 is 0. The origin for group 2 is also 0. But the group 2 distribution was a normal distribution with mean 1 and standard deviation 1.4. So the actual value 0 here is not 0, it's 1. So as we can see, the scale based on group 2 is shifted to the left by 1 because there was a mean difference of 1 between the group 1 theta distribution and the group 2 theta distribution. So this item, which has a difficulty of 2, it's located here on the scale of group 1, But if we look at the same item on the scale of group 2, now it's not 2, it's 1. But the actual meaning of that 1 is 2 because the scale is shifted to the left by 1 unit. And this is the reason that the points, the item difficulty parameter estimates were smaller for group 2. Actually, they're about 1 unit smaller than the item difficulty parameter estimates that we obtained from group 1. And the reason is because of this. The meaning of the two scales, in this case, the meaning of the origin across the two scales are different. They're not the same zero. They are different zeros. Now, the same thing happened for the unit of measurement, which is related to the standard deviation of the theta distribution. Now, let's suppose that the origin, they mean the same thing. So they're both a zero. And let's just look at the unit of measurement. So let's look at a given ability level, which is 1. Now, for group 1, the standard deviation of the theta distribution was 1, and it was set to 1. So this person here with theta equal to 1 is 1 standard deviation above the origin. But on the scale that we get from group 2, theta equals 1. It's not 1 standard deviation. And the reason is because the standard deviation of theta for group 2 was 1.4, and we set that to 1. So on this scale, 1 standard deviation is actually 0.7 standard deviation because it's 1 over 1.4. So what this means is people on the scale of group 2, they belong to a smaller range of theta. So in other words, they're cluttered around 0 compared to the thetas in group 1. So they are in a smaller range. Now it's the same item, and for an item to discriminate people in a smaller range, if we look at the ICC, that ICC should have a steeper slope at the inflection point. So this is what happens. So this solid line is the ICC for item 17 based on group 1. And the dotted line here is the ICC for the same item based on group 2. Now, because thetas lie in a smaller range for group 2, for the item to discriminate among those thetas, it should have a steeper slope. Now, the item discrimination parameter is proportional to the slope of the ICC at the inflection point. So steeper slope means larger discrimination values. So that's the reason that group 2 returned larger item discrimination parameter estimates compared to those that we get from group 1. So I'll just pause here. Are there any questions about this? Okay, then I'll move on. So again, the reason that we get two different sets of IRT parameter estimates from non-equivalent groups is because the items are on different scales. Again, the meaning of the origin and the meaning of the unit of measurement, they are different across the two scales. So we have to fix this problem, and that is where we use linking. So what we do is we set one scale as the reference scale or base scale, and we linearly transform the other scale so that it matches the scale of the reference scale. So that's what we do using linking. So again, basically what we're trying to do is we're trying to make the meaning of the origins and units of measurement identical across the two scales. And to do that, we're setting one scale as the base scale or reference scale, and we're trying to change the scale of the other group to match the base scale. So there are a lot of different linking methods out there, and some of them are based on separate calibration. So we'll talk about those methods first. So I'm going to talk about 4 methods: the mean method, the mean sigma method, the stalking lord method, and the Habara method. And after that, if we have time, I'll talk about concurrent calibration and fixed parameter calibration. So again, these methods are all based on separate calibration. What that means is, suppose we have 2 groups, and we're going to calibrate items for the 2 groups separately, independently. So we're going to feed the response data for group 1 to an IRT computer package, get the item parameter estimates, and we're going to do the same thing for the second group. So I'm going to use the term separate calibration for that case. So the basic idea is to link 2 different scales obtained from 2 non-equivalent groups. We should set one group as the reference group or base group and the other group as the focal group. And we're going to linearly transform the scale for the focal group so that it matches the scale for the reference group. And it's known that the scales are linearly related. So this is going to be the equation. This is going to be the equation that we can use to transform the scale of the focal group so that it matches the scale of the reference group. It's a linear transformation, so it has a slope A and an intercept B. And our goal is to estimate the slope A and the intercept B. Now, if the design is a common person design, then we can use this equation. But in most cases, we don't see a common person design. We see a common item design. That means we need some kind of linear transformations that uses the item parameters instead of the abilities. Now, after the linear transformation, after linearly transforming the scale for the focal group, the correct response probability should not change. So the correct response probability prior to linking and after linking should remain the same. But if we only linearly transform theta, then that's going to change the correct response probability because theta F here and theta R here are going to be different. So to make the correct response probability remain the same, what we have to do is we also have to linearly transform the item parameters. And these are the 3 linear transformations that we have to apply to the item parameters. So for the discrimination parameter, this A sub F is the discrimination parameter that we get from the focal group. We have to divide that by the slope A. then that's going to match the discrimination parameter that we get from the reference group. Now, B sub F is the item difficulty parameter that we get from the focal group. Now, to make the correct response probability remain the same, we have to linearly transform this B sub F by multiplying the slope A and adding the intercept B. So actually the linear transformation that we apply to the difficulty parameter is the same as the linear transformation that we apply to the ability theta. And the pseudo guessing parameter C, it does not change. So we're not applying any linear transformation to the guessing parameter. We only have to do it to the discrimination parameter A and the difficulty parameter B. Now, again, the goal of linking is to find the two linking constants A and B. A is the slope and B is the intercept. And what we do is, so we have two sets of item parameters, one that comes from the reference group, one comes from the focal group. And in our example, all items are common. So, but a more realistic case is that a test has both unique items and common items. So we're only going to use the common items, the item parameters for the common items to estimate A and B. So that's what we're trying to do. So with A and B, the item parameters for the focal group can be placed on the scale of the reference group using the linear transformation presented in the previous slide. So these are the three equations. Now you can forget about the last one because it doesn't do anything. You just have to remember the first two. Now, if item parameters are known, so if we know the item parameters, then the two linking constants can be found as follows. So this part here is the first equation that's up here. If we multiply the uppercase letter A on both sides and divide both sides by A sub R, then we get this equation here. So the slope A is equal to the discrimination parameter for the focal group over the discrimination parameter for the reference group. Now, this second equation here is the second linear transformation here. And to get B from this equation, we just have to move A times B sub F to the left. Then it's going to be B is equal to the difficulty parameter for the reference group minus A, which is the slope, times B sub F. Then we can get the intercept. Now, again, if we know the item parameters, which we never know, but if we know the item parameters, then it really doesn't matter which item you use to compute A and B. You're always going to get the same result. So for example, for our 40 item test with multiple choice items, suppose we know the item parameters for all 40 items. Then if we compute A based on the first item and B on the first item, that result is going to be the same as using the second item to compute A and the second item to compute B. So it doesn't matter which item we use. You can just pick one item from the 40 items and compute A and B. then we can get the slope and the intercept. Again, this is when we know the item parameters. And again, we never know the item parameters. So in practice, we only have the item parameter estimates. We don't know the item parameters. We only have the estimates. In this case, it really matters which item we use to compute the slope A and the intercept B. In other words, different items are going to give us different values for the slope A and the intercept B. Then the question is, which item should we use? We have 40 items. Each item is going to give us a different slope and intercept. Then which one should we use? So instead of just choosing a single item to compute the slope A and the intercept B, what we do is we use all 40 items. So we use all the common items in the data set to estimate the slope A and the intercept B. So how do we do that? So there are 4 different ways to do it. Again, the first one is the mean method. The second one is the mean sigma method. The third one is stalking Lord. And the last one is the Habara method. Now let's go back to the 2 linear transformations. So we have this one here and this one here. We have 2 linear transformations. And let's just multiply the slope on both sides. Then we get the one on the right-hand side. So the slope times the discrimination parameter for the reference group is equal to the discrimination parameter for the focal group. Now, from the second linear transformation, if we move A times B sub F to the left-hand side, then we get this expression. Now, instead of using a single item to compute A and B, we're going to use all items, all common items in the data set to compute A and B. So how do we do that? Again, this part here is the same as this part here. Now, to use all items, one thing we can do is we can take the expected value on both sides. So what we're doing is we're computing the average of A sub R and A sub F. In our example, we have 40 items, so we're going to have 40 A sub Rs, one for each item that comes from the reference group. We also have 40 A sub Fs, one for each item that comes from the focal group. Now let's take the average. So we take the expected value on both sides. And we are not using the parameters. Now we're using the parameter estimates. That's the reason we have this hat symbol above the lowercase letter a. Now, expectation is a linear operator. What that means is if there's a constant multiplied to the estimate, then we can bring it out of the expectation sign. So that's what I did here. The slope, which was multiplied to A sub R hat, it comes out of the parenthesis. And the right-hand side is the same. Now we have A here, the slope. This is one of the values that we want to estimate. So from this equation here, to find A, we simply have to divide both sides by the expected value of A sub R hat. So we get this expression here. Now, of course, when we do that, we are assuming that the expected value of A sub R hat, so the discrimination parameter estimates that we get from the reference group, their average is not 0. And that's a reasonable assumption because in IRT, A should be positive, right? So the average cannot be 0. So there's no problem here. To get B, now we use the second linear transformation. And we want to use all B's instead of a B for a single item. So we do the same thing. We take the average on both sides. When we do that, B is just a constant. It's an unknown constant. It's like a parameter. So this E here, it does nothing. Taking an average of a constant gives the constant itself. Now, the right-hand side here, expectation is a linear operator. So what that means is the difference, the expected value of the difference, we can write it as the difference of the expected values. So that is always true. And we have the constant A inside here. We can bring it out. So we get this expression here. And B is equal to the average of the item difficulty parameters that comes from the reference group minus the slope that we estimated using this equation here times the expected value of the item difficulty parameter estimates that comes from the focal group. Now, the reason that this method is called the mean method is quite obvious. It's because it uses the mean of the item discrimination parameter estimates, and it uses the mean of the item difficulty parameter estimates. So that's the reason it's called the mean method. So let's go back to our non-equivalent group example. And I found the two linking constants, A and B. Again, A is the slope, B is the intercept. I took the average of the item parameter estimates for the focal group. There are 40 items. All items are common. If I take the average, it's 1.3667. I do the same thing for the reference group, and the average is 0.9706. As we can see here that the average of the discrimination parameter estimates for the focal group is larger than the reference group because of the reason that I talked about earlier. So the slope is estimated as 1.4082. Now to estimate the intercept B, I first took the average of the difficulty parameter estimates for the reference group, and I took the average of the difficulty parameter estimates for the focal group, and I multiplied A, which is 1.4082, and I did the math, and it turns out to be 0.9617. Now, what we can do is we can apply these two numbers. So we can use these two numbers, one for A and one for B, to transform the item parameter estimates. So again, I have 40 items, but I only did it for the first item. And this was the linear transformation equation that we saw before. So it's the item discrimination parameter estimates for the focal group divided by the slope A that we just found. And that's going to give us an item discrimination parameter estimate that is on the scale of the reference group. Now, because we're dealing with estimates, after this linear transformation, the A hat is not going to be equal to the A hat we get from the reference group. They are going to be slightly different. So that's the reason there's a star here. So the symbol star indicates that they are the linked item parameter estimates, not the original parameter estimates for group 1, which are A, R hat, and B, R hat. So A hat it's 1.6841, and I divide it by A that we just found, which is 1.4082, then we get 1.1959. Now, the item discrimination parameter for the first item that comes from the reference group is 1.2656. So as we can see, there are slightly different, but after linking, it's much closer. So the initial item discrimination parameter was 1.6841, but now it's 1.1959, which is much closer to the item discrimination parameter estimate that we get from the reference group. Now we can do something similar to get the item difficulty parameter estimate. So we use the second linear transformation, which is the slope times b plus the intercept b. Now A is again 1.4082. The item parameter difficulty parameter estimate for the first item that we get from the focal group is negative 2.0814. So we multiply those two numbers and add the intercept B, which is 0.9617. Then we get negative 1.9693. Now, the initial item difficulty parameter estimate was negative 2.0814, but now it's negative 1.9693. And as we can see, it got closer to the item difficulty parameter estimate that we get from the reference group. So I applied it to all 40 items, and I plotted the discrimination parameter estimates and the difficulty parameter estimates. So the parameter estimates for group 1, they don't change because group 1 is the reference group. The only change happens for the item parameter estimates for group 2. Before linking, these points were above the identity line, but after linking, they are now close to the identity line. The difficulty parameter estimates, they were all below the identity line, but after linking, as we can see, they are really close to the identity line. So it seems that linking was successful. Now, the second method is the mean sigma method. And instead of using the mean of the item discrimination parameter and the mean of the item difficulty parameter, now it uses the mean of the item difficulty parameter and the standard deviation of the item difficulty parameter. So the mean sigma method only uses the item difficulty parameters. It does not use the item discrimination parameters like the mean method. So let's substitute the parameter values with their estimates because we only know the estimates, and take the mean and variance on the equation, these two equations. And these are the two. So the mean sigma method only uses the second linear transformation. It does not use the first one. So by first one, I mean this one here. It does not use this one. The mean sigma method only uses the second linear transformation. And the reason is because if we look at the first one, it involves the item discrimination parameters, but the mean sigma method only uses the item difficulty parameters, which is included in this second linear transformation. So what we do is we take the variance of this first linear transformation and we take the mean of this second linear transformation. Actually, these two are the same. So the only difference between these two is I moved A times BF to the left, then we get this equation. So basically they're the same equation. So let's take the variance of this first equation on both sides. So the variance of B sub R hat is equal to the variance of the slope times B sub F hat plus the intercept. Now the left-hand side is the same. The right-hand side here, so B is a constant, and constant does nothing to a variance. So if we add a constant to something, it's going to move the center, which is going to change the mean, but the variance of the data is going to remain the same. So we can get rid of it. Now this slope A, it can come out of the variance sign, but it comes out as a square. And that's because of the definition of variance. Variance is the expected square deviation. So we have a square up here. Now, to get A, we have to take the square root. So if we take the square root of both sides, then A, the slope is going to be equal to the square root of the variance. Sorry, the square root of the variance on the left-hand side, which is the standard deviation divided by the standard deviation of this variance here. So we get the slope A. Now let's take the expected value, the average on the second equation. So if we do that, now B is a constant and the expected value does nothing to a constant, so it comes out as itself. And if we look at the right-hand side, it's the expected value of a difference. And expected value is a linear operator. So the expected value of a difference is the difference between the two expected values. And A, again, can come out of the expected value. So this is the equation we get. So as we can see here, to get A, we only use the standard deviations of the item difficulty parameter estimates. And to get the intercept, we only use the mean of the item difficulty parameter estimates. So that's where the name came from, mean sigma method. Now let's apply the mean sigma method to our data, to the non-equivalent group scenario. So to get A, it's the ratio between two standard deviations. So I went to the data set and I computed the standard deviation of the item difficulty parameter estimates for the reference group and the focal group, and I got 1.3649. To get the intercept, I computed the mean of the item difficulty parameter estimates. Then I plugged those averages and A that's up here into this equation. Then we get 0.9305. Now, as we can see here, these numbers are different from the numbers that we get from the mean method. And the mean sigma and the mean method, they both share this equation here. But if you compare the two values, they are different. And the reason that they are different is because the way that A is computed. So in the mean method, A is computed using the mean of the item discrimination parameter estimate. But for the mean sigma method, they are computed using the standard deviations of the item difficulty parameter estimates. So even though the equations are exactly the same, the numbers that we get from those equations are different. So after getting the linking constants A and B, I applied it to the first item. So again, the item discrimination parameter estimate for the first item that comes from the focal group is 1.6841 and divided by A, which is 1.3649, then we get 1.2339. Again, the initial item discrimination parameter estimate was 1.6841. And the item discrimination parameter estimate that we get from the reference group is 1.2656. There was some difference between these two, but after linking, they became much closer. Now for B, I just plugged in all the numbers into this equation, then we get negative 1.9103. Now the initial item difficulty parameter estimate was negative 2.0814. The one we get from the reference group is negative 1.7739. Now after linking, it become closer to the difficulty parameter estimate that we get from the reference group. Now, I applied the linear transformations to all 40 items using the mean sigma method. And as we can see here, before linking, again, the discrimination parameter estimates were above the identity line, but now they moved around the identity line. And the same thing for the difficulty parameter estimates. They were below the identity line, but now they are close to the identity line. So in the chat box, someone asked which method is more accurate between the mean and mean sigma method. I'm not sure if these two methods are used in practice. People usually use the stalking norm method. But comparing the item discrimination parameter and the item difficulty parameter, it's easier to estimate the item difficulty parameter. So we might get more stable results for the item difficulty parameter estimates. So that's might be one reason that people say that the mean sigma method provides better results than the mean method. Because mean sigma method only uses the item difficulty parameter estimates. I hope that answers your question. Okay, so the characteristic curve methods. Before talking about the characteristic curve methods, let's take a break till 2:05. So I'll give you about 8 minutes to take a break, and I'll continue at 2:05. Okay, I'll continue. So we talked about the mean method and the mean sigma method, and both of these methods, they consider one item parameter at a time. So what that means is for the mean method to compute the slope, the uppercase letter A, it only uses the mean of the item discrimination parameter estimates. To compute B, the uppercase letter B, it only uses the item difficulty parameter estimates. And for the mean sigma method, it only uses the item difficulty parameter estimates. So there are other methods that actually uses all item parameters at the same time. And two of those methods are the Stalking-Lord method and the Habara method, and they are both referred to as the characteristic curve method. So one is based on the test characteristic curve, and the other one is based on the item characteristic curve. So that's the reason they are both referred to as the characteristic curve methods. Now, between the two, I'm not quite sure which one performs better, but I think stalking lord method is used more in practice. So the stalking lord method, is based on the test characteristic curve. So the stalking lord method seeks the values of A and B, the slope A and the intercept B in our linear transformations that minimize the difference between the test characteristic curves for the reference form and the linearly transformed focal form. So we have two TCCs. One comes from the reference form and one comes from the focal form. And we're trying to find the A and B that makes the distance between those TCCs, that minimizes the distance between the two TCCs. So this is the equation here. If we look inside the square bracket, the first one here, so this part here, the probability of correct response for item J, it's summed across all items. So this is going to be the TCC. And it's based on the item parameters estimates from the reference form. So this is going to be the TCC that we get from the reference form. Now, one thing you have to be careful here is I said it's across all items, but technically it's across all common items. So we don't use the unique items because they are unique to forms. We only use common items that appear on both forms. Now the second part here, it's also summed over all the common items. And this part here, the probability of correct response, it's the ICC. Now it comes from the focal form because it uses the item parameter estimates for the focal form, but it does not use the original item parameter estimates. It uses the linked item parameter estimates. And we take the difference between these two TCCs at a given theta level, take the square, and we edit across multiple theta values. So that's the stalking lord function. And we're trying to find A and B that minimizes this stalking lord function here. Now, adding the ICCs over common items, that's no problem because we only have a certain number of common items. But this part here can be a problem because theta, we have infinitely many theta values. So we cannot add the square difference between the two TCCs across all possible theta values. That's impossible. So what people usually do is they just pick a certain number of thetas in a range of theta values. For example, between -4 and 4, choose equally spaced 41 theta values. Then we only have 41 theta values, and you can compute this square difference for each theta value. You're going to get 41 of them, one for each theta value, then you can sum them. Of course, each theta value is going to have a different weight, right? For example, theta close to 0 is going to have more weight, which means there are going to be more people with that theta value compared to a theta value, for example, -4. So what people also do is when they sum over the theta values, they multiply a weight. And that weight is related to the number of people at each theta value. Now, then how do we find A and B from this stalking lord equation? we have to use calculus. So we're trying to find A and B that minimizes this square difference. So the first thing we have to do is we have to take the derivative of this function with respect to A and B. Then we're going to have two equations, one for A and one for B. We set the two equations to 0, and we have to solve the two equations at the same time using a root finding method such as the Newton's method. So that's how we can find the two linking constants A and B. But of course, there are many R functions out there that supports the Stalking-Lord method, so you can use one of them. Now, the Habara method, the Stalking-Lord method is based on the test characteristic curve, and the Habara method is based on the item characteristic curve. So the Habara method seeks the values of A and B that minimize the difference between the item characteristic curves for the reference form and the linearly transformed focal form. So if we look at this equation here, it's really similar to the Stalking-Lord function, but it's slightly different. The difference is this summation sign here. So for the Stalking-Lord method, it was inside the square bracket, but now it's outside the square bracket. So the Habara method, if we look at this correct response probability based on the reference form, this is the ICC for item J. I'm sorry, there's a typo here. There should be a J here. And this is the ICC for the same item that we get using the linked item parameter estimates. So we take the difference, square it, then we sum the squared difference over all the common items. So inside the square bracket, these two are the ICCs. So that's the reason people say that the Habara method is based on the item characteristic curve. So we do it for each theta level. And again, because it's impossible to do it for all possible theta values, we just pick a certain number of thetas in a range, and we sum it over those theta values. And theta values can have different weights, so we can also multiply the weight to this function here. Now, the two linking constants A and B, they can be found in a similar way as the Stalking-Lord method. So take the first derivative with respect to A and B, the uppercase letter A and B, set them to 0, and use the Newton's method to find A and B that satisfies the two equations. Now, of course, I didn't do that. I used existing computer package called ST. I think it stands for scale transformation. So if you go to University of Iowa, CASMA's web page, there is a page that has a lot of computer packages. ST program is one of them. I believe it was written by Dr. Cullen and another person. So for scenario 2, the non-equivalent groups scenario, the linking constants that I got from the computer package ST are as follows. Now, the mean method and the mean sigma method, if you compare, so the first values are B, these are the intercepts, and the second values are the slopes, which are A. If you compare these A and B to the A and Bs in the previous line, they're exactly the same. So that's how these were computed. Now, Stalking-Lord method and Habara method, we need to use calculus, and this is how they were computed. Now, as we can see, the intercept values across the 4 methods, they are slightly different, and the slope values are also different. And different methods always provide different results, so it's not surprising. Now, using the Stalking-Lord linking constants, I applied the A and B, these two numbers here, So B is 0.9410 and the A is 1.3735. I applied it to item 1, like the mean and mean sigma method. Now again, the discrimination parameter estimate for item 1 is 1.6841. I divided by A that I got from the Stocking-Lord method, which is 1.3735. Then we get 1.2261. Again, the initial discrimination parameter estimate was 1.6841, but now it's 1.2261, which is much closer to the discrimination parameter estimate that we get from the reference group. Now the item difficulty parameter estimate, I use this equation using the linking constants that I got from the Stocking-Lord method. And A was again 1.3735, B is 0.9411. The original difficulty parameter estimate is negative 2.0814. After linking, it's negative 1.9177, and it got closer to the difficulty parameter estimate that we get from the reference group. And if we apply the Stocking-Lord linking constants to all 40 items, then we get these two figures. So for the discrimination parameter estimates, they were all above the identity line, but now they are scattered around the identity line. And the difficulty parameter estimates, they were below the identity line before linking, but after linking, now they are scattered around the identity line. So now it seems that the two scales, the scale that we get from group 1, which is the reference group, and the scale that we get from group 2, which is the focal group, now the two scales are, they match each other. So in that sense, now the item parameter estimates for group 2, which is the focal group, is on the scale of the reference group, which is group 1. Now, one other thing we can do with the linking constants A and B is, for the focal group, even though the distribution was not a standard normal, a normal 0, 1, the computer package set the distribution to normal 0, 1. So what we can do using the linking constants A and B is we can estimate the distribution of the focal group. And I'll talk about how to do that. So IRT computer packages, they set the distribution of theta to a standard normal distribution. Now, we know this linear transformation. So theta F is the theta that we get from the focal group. It's our initial thetas, the thetas that we get before linking. And theta R star are the thetas that we get after linking. Now here, theta F, our initial thetas, it was assumed that they come from a standard normal distribution. So using these two pieces of information, we can actually find the mean of theta sub R star and the standard deviation of theta R star. So it's down here. To get the mean, we just have to take the mean on both sides. So take the mean of theta R star and also take the mean of A times theta sub F plus B. Now, if we look at this part here, again, expectation is a linear operator. So the constant that is multiplied to the variable can come out of the expectation sign. And the constant that is added to the term that includes the variable of interest can come out of the expectation sign. Now, the expected value of theta F, initially it was assumed to be 0. So just plug in 0. Then this part goes away. The only thing that is left is B. So the expected value of theta sub r star, the theta of the focal group after linking is b. Now, to get the standard deviation, we just have to take the standard deviation on both sides. So that's what I did here. Now, the standard deviation does not change by adding a constant, so this part goes away. A comes out as itself because it's the standard deviation. If it's the variance, it comes out as a square, but for standard deviation, it comes out as a. Now the standard deviation of theta f was initially set to 1, so a times 1 is a. So what this means is after linking, the distribution of theta for the focal group is estimated to follow a normal distribution with a mean of b, which is the intercept, and a, which is the slope. So let's apply this to using the linking constants that we got from the Stalking-Lord method. So again, the expected value of theta after linking for the focal group, even though the subscript here is r, is the focal group on the scale of the reference group, it's a times the expected value of the initial theta, which is 0 plus b. So this term here goes away. The only thing that's left is b, so it's 0.9411. The standard deviation of theta sub r star, it's a times the standard deviation of theta sub f, which is initially set to 1. So it's a, which is 1.3735. So after linking, we recovered the distribution of the focal group, and it was estimated as a normal distribution with a mean of 0.94 and a standard deviation of 1.37. Now, the distribution I used to generate the response data for the focal group is normal 1, mean of 1, and a standard deviation of 1.4. So these are the true values. And as we can see, the estimates here are pretty close to the true mean and true standard deviation. Now, so in our example, I assume that all 40 items are common items. But a more realistic case is when forms, they have both unique items and common items. So if we look at this picture here, so we have two groups. Group 1 took form 1, group 2 took form 2. Now the two forms, they share some common items, but they also have unique items. So in this case, how do we do linking? So for our example, because all 40 items were common items, I used all 40 items to compute the linking constants A and B for all 4 linking methods. But here we cannot do that because we have some unique items. So in that case, what we can do is we can use the common items to estimate the slope A and the intercept B using any one of the 4 linking methods. So mean sigma, Stalking-Lord, Habara, doesn't matter. Just apply those equations using the common items. Then we find A and B. Then what we do is we apply the linear transformations with the estimated slope and intercept to all items. Then the item parameter estimates for all items for group 2, assuming that group 2 is the focal group, is going to be on the same scale as the items for group 1. So that's the more realistic case. So one case when all items are going to be common is when you look for differential item functioning. So in that case, we're giving the same item to the same test to two different groups of people. So if that's the case, all items are common. And if we believe that the two groups are non-equivalent, then we first have to do linking before testing for differential item functioning. So that might be one case when all items are common. But in many other cases, this is a more realistic scenario when we have both unique items and common items. Okay. So are there any questions? Okay, so we have about 30 minutes left. So I'll briefly talk about concurrent calibration and fixed parameter calibration. Now, these two calibration methods are also used to link two different scales. And they are studied a lot. So let's talk about them. Now, for separate calibration, so the mean, sigma, Stockian, lower than Habara method, after we calibrated the items, we used the post-hoc linking method to place the items on the same scale. And the reason that we needed a post-hoc linking method is because the distributions of theta for all groups were set to the same distribution, although they are non-equivalent groups. So that's the reason we use the post-hoc linking method. Now, then the question is, okay, so the reason that we needed a post-hoc linking method is because all distributions of theta were set to the same distribution. Then during the calibration, if we can estimate the distribution of the focal group relative to the distribution of the reference group, which is often set to a standard normal distribution, then we might not need a post-hoc linking method. So we're estimating the distribution of the focal group along with the items and use that distribution to estimate the item parameters for the focal group. Then after the calibration, we can expect the item parameter estimates for the focal group to be on the scale of the reference group. Now that's the basic idea behind concurrent calibration. So instead of setting the two distributions to the same standard normal distribution, we're going to set the distribution for the focal group to a standard normal distribution to set the scale. And we're going to estimate the distribution for the focal group relative to the reference group. And use that distribution to estimate the item parameters. That's what concurrent calibration does. So the procedure is initially the distributions of theta for the reference and focal groups, they are all set to a standard normal distribution. And the reason we do this is because, again, theta is a latent variable, so we don't know the distribution. Now we have to set the scale, the theta scale. So for the reference group, we're going to use a standard normal distribution to set the scale. For the focal group, we don't have any information about the theta distribution, so we're also going to set it to a standard normal distribution. Now, item parameter estimates are updated using response data and distributions of theta. Now, for common items, concurrent calibration uses response data and distributions of theta for both groups, so both the reference and focal groups. Because the items are common because they appeared on both forms, the form that the reference group took and the form that the focal group took. So we're going to use all those information to update the item parameter estimates for the common items. But for the unique items, they are unique to a form. So what concurrent calibration does is it uses the response data and distribution of data for the group that took the items to update the item parameter estimates. So the amount of information that items use are going to be different between common items and unique items. For common items, it's going to use information that comes from both groups, but for unique items, it's only going to use the information that comes from the group that took the unique items. So this way, we update the item parameter estimates for all items. Then the distribution of theta for the focal group is updated using the updated item parameter estimates. And the expected number of people at each quadrature point computed in the E step of the marginal maximum likelihood estimation via EM algorithm. So the most common estimation method for estimating the item parameters is the MMLE via EM algorithm. So that has two steps. The first step is called the E step, and the second step is called the M step. In the E step, we compute the expected number of people at each quadrature point. So that means we have a lot of theta values. We can't find the number of people at each theta value. So what we do is we pick a certain number of theta values that belongs to a certain range. For example, FlexMert uses 49 quadrature points. That means 49 theta values between -6 and 6. And it computes the expected number of people at each of those 49 theta values. And that's computed in the E step. So if we combine that information with the updated item parameter estimates for the focal group, then we can update the distribution of theta for the focal group. So initially it is set to a standard normal distribution, but it's going to keep update, and now it's going to move away from a standard normal distribution. Now steps 2 and 3 are repeated using the updated item parameter estimates for both groups and the updated distribution of theta for the focal group until the convergence criterion is met. Now, the distribution of theta for the reference group, it does not change. It's always going to be a standard normal. Only the theta distribution for the focal group is going to be estimated relative to the distribution for the reference group. So it's like, okay, we don't really know what the theta distribution for the reference group is, but let's just set it to a standard normal distribution. Then what would be the distribution of the focal group? And to answer that question, we are estimating the distribution of theta for the focal group using the information we have, which is the item parameter estimates and the expected number of people at each quadrature point. So for the non-equivalent group case, I calibrated the two response items using the computer package FlexMert. So FlexMert supports concurrent calibration. Almost all IRT computer packages, they support concurrent calibration. Now, in our example, all 40 items are common items. So we're only going to get a single set of item parameter estimates because, again, all items are common. And as we saw here, for common items, concurrent calibration uses response data and distributions of theta for both groups to update the item parameter estimate. So it's going to combine the information that comes from the reference group and the focal group, and it's only going to provide a single set of item parameter estimates for the common items. For the unique items, we're going to get different item parameter estimates for different unique items. So I didn't display the item parameter estimates on this slide. Instead, in the FlexMert output, we get the group parameter estimates. Now, group 1 is the focal group. The mean is 0. The standard deviation is 1. S2 is the variance. As we can see here, FlexMart did not estimate the distribution of theta for group 1, again, which is the reference group. It was set to a normal distribution with mean 0 and standard deviation 1. If we look at the mean and standard deviation for group 2, which is the focal group, the mean was estimated as 0.97 and the standard deviation was estimated as 1.46. So as we can see here, FlexMart, when running concurrent calibration, it estimated the distribution of theta for group 2, and the final estimate came out as a normal distribution with mean 0.97 and a standard deviation of 1.46. Now, I said that the true values are 1 and 1.4. So the true mean is 1, the true standard deviation is 1.4. And as we can see here, the estimates are pretty close to the true values. In concurrent calibration, used this distribution to estimate the item parameters for the focal group and also for the common items. So the next one is fixed parameter calibration. And this is used a lot to calibrate field test items. When the item parameter estimates for the operational items are known. So that's when fixed parameter calibration is used a lot. So it's used a lot in the context of CAT, computerized adaptive testing. Because all operational items, they already have item parameter estimates, but there are some field items that testing companies are trying to test, and we want to get item parameter estimates for those field test items. In that case, we can use fixed parameter calibration. So the basic idea of fixed parameter calibration is similar to that of concurrent calibration. So what that means is we're trying to estimate the distribution of theta for the focal group and use that estimated distribution to estimate the item parameters. Then what's the difference between concurrent calibration and fixed parameter calibration? So the main difference is in fixed parameter calibration is a single group calibration, whereas concurrent calibration is a multiple group calibration. So in fixed parameter calibration, we are only calibrating the items for the focal group. And when we do that, we fix something. We fix the item parameter estimates for the common items to their existing values. So that's the reason it's called fixed parameter calibration. Basically, we're only estimating the item parameters for the unique items. The item parameter estimates for the common items, they are fixed to their existing values. Now, concurrent calibration, it's not how concurrent calibration works. It's a multiple group calibration. So we are calibrating items for the reference group and focal group at the same time. That's the reason it's called concurrent calibration. So in the context of CAD, again, so all operational items, they have existing item parameter estimates, so we can fix them to their existing values and use that information to estimate the parameters for the field test items. So initially, distribution of theta for the focal group is set to a standard normal distribution. Because again, theta is a latent variable and we really don't know the distribution of theta. But we're trying to update this standard normal distribution so that we get a distribution that gets close to the true distribution, whatever that is. So parameters for the unique items are updated using item responses and distribution of theta. The parameter estimates for the common items, they are fixed to their existing values, so they are not estimated. Now the distribution of theta is updated using the updated item parameter estimates for the unique items and also the fixed common items, and the expected number of people at each quadrature point that we get from the MMLE via EM algorithm. And we repeat these two steps until the convergence criterion is met. Now, in this example, there's really no reason to run fixed parameter calibration because all items are common. So that's the reason I didn't include any results of fixed parameter calibration. But if your test has both common and unique items, then fixed parameter calibration is an option to link the unique items to the scale of the common items. Okay, again, the conclusion is linking is a statistical procedure that adjusts for group differences in IRT. So the reason that item parameter estimates are on two different scales after separate calibration is because they are on two different, because what happened is even though the groups are non-equivalent, we set the ability distribution for the two non-equivalent groups to the same standard normal distribution. So that's where the problem started. So we're trying to adjust that problem. So we can think linking as a procedure for adjusting group difference in IRT. Now, equating is a statistical procedure that adjusts for differences in form difficulty. So, and when we say equating, we actually deal with raw scores. So for example, SAT math, it's administered multiple times throughout a year. Now, if two different students took the SAT math on two different test dates, they can get the same score, for example, 40, the raw score 40, but the raw score 40 might not mean the same proficiency level. And the reason is because one form might be easier than the other. If that's the case, then the student who got 40 taking the difficult form is more proficient than the student who got 40 taking the easier form. So equating is a statistical procedure that adjusts for differences in form difficulty in that sense, and it only applies to raw scores. So in IRT, the score is ability theta. So applying equating to theta really doesn't make sense because of the invariance property. So the invariance property says that the item parameters are group invariant, but also if two different tests are supposed to measure the same construct, then think about a single person. It doesn't matter which test that person takes, that person should get the same theta, right? So the form difficulty really does not affect theta because of the IRT invariance property, but that's not the case for raw scores. So when we say equating, we mean raw scores. So that's it. If you have any questions, I'm happy to answer the questions. Okay, so I got a question in concurrent calibration. How does the common items work in computing the focal group distribution? So the item parameter estimates for the common items, they come from both the reference and focal groups. We only get one set of item parameter estimates. And actually, the common items, they have the information of the scale for the reference group. So when we update the distribution of theta for the focal group, we use both the common items and the unique items for the focal group. And again, the information of the scale of the reference group, it's included in the item parameter estimates for the common items. So you can think it like this. So we have the item parameter estimates for the common items. We have the response that comes from the focal group. Now, comparing those two, we can estimate the distribution of theta. For example, if the common items are all difficult, and we looked at the response data that we get from the focal group, and there were a lot of ones, that means that focal group is able. So in that sense, the theta distribution is going to be estimated to be high. Does that make sense? So in concurrent calibration, no, forms can have different number of items. Yes. So the forms, they don't need to have the same number of items. So for example, if form 1 has 20 unique items and 20 common items, and form 2 has the same 20 common items and 30 unique items, we can still use concurrent calibration. Then we're going to get, for the unique items in form 1, there are 20 items. So we're going to get the item parameter estimates for those 20 items. We're going to get the item parameter estimates for the 20 common items, and we're going to get 30 item parameter estimates for the unique items that are included in form 2. So in reality, when we don't know the true item parameters and thetas, how could we evaluate the performance of the concurrent calibration and other linking methods? So in the literature, there are a lot of research studies that compare different linking methods. And I won't say all, but most of them, they use a simulation study. So when we use a simulation study, we're the god, right? So we know all the item parameters, we know all the thetas, so we can make comparison. But using real data, it's not easy to compare different linking methods based on a single data set. Now, how many common items between forms are sufficient for linking? So Dr. Brennan, Colin and Brennan, they say between 20% and 40%. I think it's between 20 and 40. So if we have too many common items, the problem is we're exposing too many items to the students. And if we have we only have a small number of common items, then the problem is that the linking results we get from the common items might be unstable. So it's between 20 and 40. And many studies, they did a simulation study and they used 20%, 30%, and 40%. And many studies show that using 20% common items is sufficient. But of course, for some tests, 20% can only be 2 items, right? If that's the case, we might need more common items. So for a 40 item test, 20% is 8 items. That might be sufficient, but for a 10 item test, 20% is only 2 items, then that might be problematic. So it's more related to the number of common items than the proportion of common items. To develop a big vertical scale for K-12, which linking method would you recommend? So I'm not sure if I can recommend any linking method, but in vertical scaling, I think many people use the concurrent calibration method. Because in vertical scales, we're going to have data that comes from a large number of grade levels, and to calibrate them in a single run, then we can use concurrent calibration. If we use separate calibration, then what we have to do is we have to, so separate calibration, for example, mean the Stocking-Lord method, it can only be applied to 2 forms at a time. So if you're going to use Stocking-Lord method, that means you have to apply Stocking-Lord methods to 2 adjacent grade levels, depending on how many grade levels you have. But if you use concurrent calibration, then you can do it in a single run. So in a random groups design, you don't really have to do linking, because random groups design means that the groups are equivalent in terms of their theta distribution. If that's the case, after you run separate calibration, all items are already going to be on the same scale. So linking is only necessary for the common item, non-equivalent groups design. So again, linking is used to adjust for group difference. So random group design, there is no group difference. The groups are randomly equivalent. So when we estimate the item parameters separately, the item parameter estimates are already going to be on the same scale. So as long as the old form and the new form, they share common items, then yes, you can use the fixed parameter calibration method. But I think the most widely used case for fixed parameter calibration is to calibrate field test items. But there's no reason not to use fixed parameter calibration when you can use the Stocking-Lord method. So whenever you can use the Stocking-Lord method, you can use the fixed parameter calibration method. So IRT, everything is relative. So the question is, how much is the standard normal assumption important? And is there any way to check the distribution assumption before calibration? No, it's not that important. So we don't really know the distribution of the reference group. Theta is a latent variable. We're just setting it to a standard normal distribution. Now, when we estimate the distribution for the focal group, we're not trying to estimate the exact distribution. We're trying to estimate the distribution of the focal group relative to the reference group. So if the reference group distribution is a standard normal, we don't really know what distribution it follows. But if it's a standard normal distribution, then what is going to be the distribution of the focal group? So that's the question. And so another related topic is, so how do we know that it follows a normal distribution? It might not, right? So, okay, we're good with fixing the distribution of the reference group to a standard normal, but there's no guarantee that the distribution for the reference group is going to be a normal. It can be non-normal. In that case, most computer packages, they support the function to estimate the shape of the distribution. So you don't really have to assume that the distribution of the reference group follows a normal distribution. When you run concurrent calibration and fixed parameter calibration, you can ask the IRT computer package to not only estimate the mean and standard deviation, assuming a normal distribution, you can ask the program to come up with a distribution of theta without assuming normality. And that's called the empirical histogram. So if you use the empirical histogram option, for example, in FlexMert, it's going to give you actual distribution. So it's going to give you quadrature points, which are theta values, and it's going to give you the weight for each theta value. And if you plot that distribution, it's not going to be a normal distribution. So there's an option out there that you can use. Okay, so I hope I helped you understand linking. If I did not, I'm deeply sorry. I'm not sure if Dr. Stella Kim is going to give me another chance next year, but if she does, I'll promise that I'll do better. So you can come back.
I might not be able to give you another chance because I'm
Oh.
going to be stepping down next year from
Okay.
the co-chair position. So
Okay.
probably, yeah, the next one we'll probably invite you for the next one, but I don't know if I will be invited as well too.
I'll be the co-chair and I'll.
You promised me. Okay, thanks everyone for joining this session, and thanks Dr. Kim for this fantastic session. I think it was very informative and helpful to people who don't really know about the linking procedure in general. We appreciate your attendance today, and there will be another session led by Dr. Jamie Malatesta and Chris Hahn next week. So if you have signed up for this session, I hope to see you there, and have a wonderful rest of the day. Bye. And then the video will be made available through the YouTube channel of NCME. So if you go to the YouTube and just type in NCME, you can see a series of training sessions over there. And this video will be available there as well. Okay, thank you. Bye.
Bye.